Good morning. In this video, we are going to discuss two important techniques, the Fourier series and Fourier transform. Actually, I'll be discussing these two topics in a series of videos. In the first two videos, I'll be giving you the ideas about this Fourier series and Fourier transform, and then we'll consider the related problems and the applications of Fourier series and Fourier transform, and also we'll discuss the limitation of these two techniques. So let us start. This Fourier series we'll call as FS in short, and Fourier transform FT. These two techniques are basically used to compute the frequency content of signals and also for the systems. If we have the concept of frequencies for signals and systems, then we can analyze the signals and systems in frequency domain. First, we'll consider the signals. The signals these signals are nothing but some functions in one independent variable, that is from, suppose if it is xt is a signal, and that signal we can divide in two broad categories. One is periodic, other one is aperiodic. And signal will carry the information, and in the periodic signal, the signal repeats its nature in a regular interval. If we say xt is a periodic signal, then x of t plus n t naught, if we consider, then we will get again the same xt signal, means the signal xt will repeat in every t naught second, and the minimum value for t naught is called time period. Of this periodic signal. So as it is continuous and it will go for infinity, so every periodic signals are time unlimited, so they are time unlimited signal. Whereas in the aperiodic signal, there is no such characteristics. Okay, mostly they are time limited signal. However, we can also find the time unlimited aperiodic signal. Now, to find the frequency content of periodic signals, we can use Fourier series. So Fourier series will be used to find the frequency content of periodic signals, whereas the Fourier transform will be used to find the frequency content of aperiodic signals. However, The Fourier transforms technique is more general. We can also use the Fourier transform to find the frequency content of periodic signal. So Fourier series as well as Fourier transform both could be used to find the frequency content of aperiodic signal. This is for periodic signals, and this is Fourier transform should be used for aperiodic signals. Now we'll start with the Fourier series. So we'll consider first Fourier series. Now let us take few periodic signals. So this is one square wave. The amplitude suppose 1 and minus 1. So it's square wave. This side also it will exist. Okay. This is the time 0 and it is t0. This is suppose 2t0, like that. Now this signal we'll consider as x1 of t, where t0 is the time period of the square wave. Next one I'll consider the same time period t0 any like this. This is one waveform within one time period. It will repeat okay, like that. So it will continue. So this side is also there. This signal suppose it is x2. And I'll consider this signal. This is your t0, 2t0. Right. This one signal x3t. One more signal like this. Okay, time t. Now the t0 is the time period for all the periodic signals, and you notice that x1, x2, x3 and x4 all are periodic signals with the time period t0. So t0, the time period so for these periodic signals we can define the frequency. So general convention is that we can define frequency as the number of cycles in 1 second, means number of repetition in 1 second. So t0 second, in t0 second there will be one cycle. So in 1 second there will be 1 by t0 cycles. So frequency f0 is 1 upon t0, that many cycles in 1 second. So that is called the frequency in hertz. So frequency of these signals, broadly we'll say the f naught is 1 upon t naught. And this frequency is true for all the 4 signals. But the signals are obviously they are different. So only this frequency is not sufficient to characterize or differentiate these 4 signals, because within the same time interval 0 to t0, within one time period, the shapes are different. Okay, and we understand that if signal is varying smoothly, like this one, third one and fourth one, they will contain low frequency, and if signal varies rapidly, then frequency content of the signal is high. So this fundamental frequency, this f naught, is called fundamental frequency. This fundamental frequency is not sufficient to characterize the periodic signals. So we need more concept. Okay, so all the 4 will have same fundamental frequencies. Okay, but this last 2, you see, they're very smooth one. So these 2 signals, they are called as sinusoidal signals. So sinusoidal, basically there are 2 types. First one is, this is a cos signal, cos omega naught t, and it is sine omega naught t. These are the 2 signals, and we'll consider that. So this omega naught here, the omega naught is the angular frequency. It is 2 pi upon t naught, and its unit is radian per second. Okay, so these 2 signals, cos omega naught t and sin omega naught t, they are considered as the periodic signals with single frequency omega naught. So both these and this, they'll contain single frequency. Omega naught, that is angular frequency, and linear frequency is f naught, no other frequency. And difference between these 2 is that only the time shift or phase shift. So there is a time shift of t naught by 4. Just see, if it is total time t naught, then this is only the shift, the gap. This signal is shifted left side, and I will get the cos signal, or this cos signal is shifted to right side by this t naught by 4. I will get the sine wave, and t naught by 4, this total angle change is 2 pi. Okay, so 2 pi upon 4 is pi by 2. This angle is pi by 2. So there is a phase change of pi by 2. So this sine wave and cos wave, they will differ by 90-degree phase shift, but both will contain same frequency omega naught. And these 2 frequency signals will get from one very simple concept, that is simple harmonic motion. If we start with simple harmonic motion, and its relation d square x dt square is suppose minus omega naught square x. This is the relation equation for simple harmonic motion, and the solution for this equation is, general equation is A cos omega naught t and B sin omega naught t. Okay, and where omega naught is the frequency. So thus we can say that this cos signal and sine signal, they will satisfy this equation and they will have the frequency only omega naught. Okay, and their shape was very regular. So we may consider one more analogy. We can consider that there is one unit circle. Okay, and in this unit circle, suppose one point is moving in anti-clockwise direction and with the angular velocity omega naught. Okay, so in t second it will cover this angle. This angle is theta, and this theta is equals to omega naught times t. Okay, now if you take a projection of this point on this axis, okay, so this is a unit circle, so this magnitude radius is 1. So this projection, this is your cos theta, means cos omega naught t, and this component will be sin omega naught t. So the movement of this point along the x-axis, so starting from here, then here, then here, it is going to this side, then it will become 0, then again it will move to the left side, negative, then it will have negative 1, so this is minus 1, then again it will reduce, it will come to 0, and then again it will increase and go to 1. So this will complete one time period. So this cos wave starting from 1 means this is 1, and then it will become 0 gradually, then it will go to the negative side, and again it will be 1. This is one rotation. Again it will continue for the next rotations like this. So this is your cos omega naught t. And you see this is very smooth curve. And if you consider this projection, this point along this y-axis, so if this is x-axis, it is y-axis. So initially when this is the point, then the projection on this y-axis is this point. Then it is moving to the upward side. It will have maximum 1. Then again it will reduce. This means it will start from 0. Then it will have maximum. Then 0, negative, and like this. This is your sin omega naught t. So these two signals will have same frequency, omega naught, and that is the sufficient frequency, only omega naught. Okay. Now, the other periodic signals, any other periodic signals, we can find the frequency content for those signals using Fourier series. Joseph Fourier great mathematician, French mathematician, 1768 to 1830. Fourier proposed that any periodic signal can be decomposed in terms of sinusoidal signals with only fundamental frequency and their harmonics. This is important. So what it says that any periodic signal can be considered as summation of sinusoidal signals, and those sinusoidals only the fundamental frequency and harmonics. Harmonics means integer multiple of fundamental frequencies. Okay, so with this one we can say that signal xt, if it is periodic, then it can have some DC component, that is A0, and rest are AC component. Those are summation of sinusoidals. Alright, an cos n omega naught t plus bn sin n omega naught t, where n equals to 1 to infinity. All integer, n are integers, okay, and omega naught is the fundamental frequency. So you will see it may contain only fundamental frequencies or the harmonics, no other frequencies, and it is sufficient to express this periodic signal. Now here, these signals, so we'll consider these signals. One is, first one DC I'll consider first one, other one is cos omega naught t, cos 2 omega naught t, cos 3 omega naught t, all those. These are the cosine signals, with fundamental frequency and its harmonics, and sine omega naught t, sine signals, sine 2 omega naught t, sine 3 omega naught t, all those. If I consider this is a set of signals, and this set will be called as orthogonal set. So this orthogonal concept is useful. Now F1 and F2, these two signals will be called as orthogonal to each other. They are orthogonal if for certain range, if I multiply these two signals and integrate it within certain range, suppose from T1 to T2, then if this area is 0, integration is 0, then F1 and F2 are called orthogonal within the time T1 to T2. Okay, and this orthogonal concept is very useful. We can express one signal, suppose Ft, which is a composition of these two signals, F1 and F2. It's a mixture of two signals with some certain coefficient, suppose K1 times F1t and K2 times F2t. These are the two signals and they are combined with the corresponding coefficients, and I'll get one new signal ft. Now we can easily find these two coefficients k1 and k2 if f1 and f2 are orthogonal to each other. So how we can do that one? Simply, if you multiply this ft with 1, suppose f1t, and then what you will get? The both side you will get k1 f1t, so it will become f1 square t, and this will become k2 f1t times f2t. Now if you integrate both sides, and for that time interval t1 to t2, okay, so what you will get? As f1 f2 they are orthogonal to each other, so this term will vanish, it will become 0, so only the first term is left. So easily we can extract from this one, we can find the k1 easily. K1 is this one. First one is f of t and f1t dt. This time interval, okay, and this is your f1 square t dt. So similarly, you can find the k2. K2 will be f of t multiplied with f2t, because that corresponding signal, and here it is f2 square t dt. Okay. So this is a useful concept. Now in Fourier series, this is the total orthogonal set. So if you consider any two signals, they will be orthogonal to each others. Okay. So now we can exploit this concept to find these Fourier coefficients. So now this xt, as we have said, that it is expressed as this one, okay, n equal to 1 to infinity. Now we can see the orthogonality here. So first, if I consider one DC term 1 and this cos, then the product is 1 into cos, means simple cos. So cos of n omega naught t, if you integrate over one time period, I'll notate it this way, t naught, one time period t naught. So it could be from 0 to t naught or minus t naught by 2 to plus t naught by 2. Anyway, so within one time period, if you integrate it, then it will become 0, because any cos signal within one time period, so total positive and all negative, this is for only cos omega naught t. So this is positive and this is negative. So positive part and negative part, they are same but opposite sign, so total area will become 0. Now if I consider cos 2 omega naught t, so within the same time period t naught, so this is your t naught, I will have double frequencies, means two repetitions, okay, like this, and again we'll have this one. So again you will see total positive up to this positive, and total negative will remain the same. So again, cos 2 omega naught t, its area is also 0 within one time period. So same is true for sine. For one time period. And then if I consider two cos signals, two different cos signals, okay? So cos n omega naught t, another one is cos m omega naught t. Then if you integrate it, what time period t, then this will be 0 again for m not equal to n. And if m equals to n, then it will become same cos square. So it will become same cos square, and obviously area cannot be 0 because any square means positive, and if we integrate the square signal, it will have a non-zero value. Okay, and this cos squared signal you can express as cos squared theta, as this is 2 cos squared theta equals to 1 plus cos 2 theta. So this area will be again 0. So only this will be there. So that's how integration area will be t, and this 2 will come here. So t by 2. So you can compute this one. Simply it will be t naught by 2. Okay, for m equal to n. Similarly, fourth one, if I consider two sine signals, sine m omega naught t and sine n omega naught t dt, again it will be 0 for m not equal to n, and this is equals to t naught by 2 for m equal to n. Okay, because if we multiply two sine signals, then if they are different, then again we can combine sine of a cos of a plus b minus cos of a minus b. So two cos signals, and as m and n are integers, so again we'll have two cosine signals with the harmonics only, and their individual integration is 0. That's how the first term will become 0, and second term is become non-zero because they are remaining the same. We will get square term, and again sine squared 2 sine squared theta we can write as 1 minus cos of 2 theta. Okay, now fifth one, if I consider one sine one cos, okay, so cos n omega naught t and sine m omega naught t dt for one time period, and it is always 0, because this one, if they are same or not doesn't matter. If they are not same, then I can consider sine of a plus b plus sine of a minus b form. Individual they will become 0, and if they are same, then I will get sine of 2 theta form. Again it will become 0. Okay, so the sinusoidals and DC, they are orthogonal to each others. So now we can extract those coefficients say 0. So you see, the originally is we had this expression a0 plus n cos n omega naught t plus bn sin n omega naught t. Okay, n equals to 1 to infinity. Now if I multiply both sides by, simply if we take integration, so first one, if I integrate this signal both sides over one time period t, that's all. So this signal will become 0, and only a0 will remain same, So A0, so eventually it is A0 outside, and area, so this will become dt only time 0 t0. So it is A0 and it is t integration 0 to, suppose I am considering 0 to t0. So the duration is t0, so A0 into t0. So from this one, we can find that A0 is 1 upon t0, it is xt dt for one time period t0. So this is your average value of the signal xt. Now, if I multiply both sides first by cos of n omega naught t, then when that cos n omega naught t will match with that corresponding cosine terms, then only I'll get square, otherwise I'll have some other sinusoidals. And then if you integrate this one, every one will become 0 except that term. So if I first multiply xt with cos n omega naught t and then integrate over one time period, then only with the cos of n omega naught t, that coefficient is an, that will remain, sorry, an, and then it is become cos square same, and we have already shown that its integration value will become t0 upon 2. So an will be 2 upon t naught xt cos n omega naught t dt for one time period. And similarly, if you multiply both sides with sin n omega naught t and then integrate over one time period t naught, then I will get bn term, bn into t0 by 2. So bn will be 2 upon t0 xt sine of omega naught n omega naught t, okay, and dt. So this is the total. So you see I have got all the three terms, A0, An and Bn. A0 is simply average 1 upon t0 integration x of t dt for one time 0. And this is 2 upon t0 xt cos n omega naught t dt or one time period. This is again 2 upon t0 xt sin n omega naught t dt what time t0. Okay, so this is a trigonometric form with the help of sinusoidal signals. Now the signals, every signal sine and cos, we can again rewrite in terms of exponential forms using Euler's theorem. So you know that cos theta is e to the power j theta plus e to the power minus j theta upon 2, and sin theta equals to e to the power j theta minus e to the power minus j theta upon 2j. Okay. Now if you use this concept, then every cos means cos n omega naught t will contain these two terms, e to the power j n omega naught t plus e to the power minus j n omega naught t upon 2, and sin n omega naught t. Similarly, it will contain again two terms by 2j. So you see, sin and cos we can replace with e to the power j n omega naught t or e to the power minus j omega t. And okay, so I can say that the periodic signal xt can be decomposed in terms of exponential only, and in that case we'll have this form e to the power j n omega naught t, and n could be positive or negative. So n is minus infinity to infinity, all integers. Okay, and the coefficient, suppose it is Cn. Okay, so here the set, what is set? So if n equal to 0, e to the power 0 is 1. Then for positive it will be e to the power j omega naught t, e to the power j 2 omega naught t, like that. And negative, it is e to the minus j omega naught t minus j 2 omega naught t, like that. This set we are considering. Now how to extract this Cn? Now here one important thing is that they are orthogonals. Okay, so you see, integration of e to the power j n omega naught t what time period t0, it has become 0. Whether n is positive or negative doesn't matter. Okay, and e to the power j m omega naught t times e to the power j n omega naught t, what one time period, if we integrate it. Now if m and n, they are different, okay, then we can combine these two together, m plus n. Okay, these two I can combine, e to the power j m plus n omega naught t dt, one time period. Now you see, this will be again, it will remain 0 if this is not equal to 0. M plus n not equal to 0 means this is equal to 0 for m not equal to minus n. Okay, and when m equal to minus n, then it will become 0. The t by 0 is 1, then integration is only t means the duration t0 for m equals to minus n. That is the important concept. So m equal to minus n, it is only t0. Other than this, everywhere it is 0. Okay, that means to extract the Cn, we have to multiply both sides with its negative component, e to the power minus j n omega naught t. Okay, so what will happen? With this xt, we will multiply e to the power minus j n omega naught t, and then we will integrate it for one time period t naught. What we will get? We'll match with the Cn only, and that time the integration value will become only t0. Okay, so from here we can calculate Cn. Cn is 1 upon t0 x of t e to the power minus j n omega naught t dt. Okay, so we'll continue this one. Then we'll find next, we'll try to find some properties or some symmetrical properties of the signals to find these coefficient Cn's. some odd symmetry, even symmetry, half-wave symmetry, and some special techniques how to compute the Cn efficiently. Okay,